So next topic will be characteristics and the application of a DC motor. If I want to consider with the different types of DC motors, the shunt type of DC motor will have series type, cumulative compound and a differential compound. If you are going to consider for the shunt type of motor, the main characteristic will be speed is fairly constant and it will have a medium starting torque. And the application, it will be used in the blowers, fans, centrifugal pumps, a lathe machine, drilling machine. In all these places, shunt DC motors will be used. If you consider for the series motor, it has a high starting torque and we cannot start this series motor in case of a no load condition. It will be very dangerous and we can vary the speed of a DC series motor, so it is a variable speed motor. So the applications will be cranes, in the elevators, trolleys, locomotives, conveyors. In all these places they are going to use with the DC series motor. Now if you go with the cumulative compound type, it has a high starting torque characteristics and on no load condition it cannot be used. The applications of cumulative compound motors are rolling mills, heavy planners, elevators, etc. If you go with the differential compound motor, as the speed increases, as the load increases, the speed of the motor increases. That is the main characteristics of a differential compound motor. So which is usually not possible. That's why the practical application is not suitable for this type of a motor. Then let us discuss about the characteristics of a DC motor. So whenever we want to discuss about the characteristics of DC motor, there will be majorly three major characteristics. One is a torque versus armature current, which is also called as electrical characteristics. Then speed versus armature current characteristics, and the last one will be a speed versus the torque characteristics, which is called as a mechanical characteristics. So from the equation of a torque, we know that torque is given by 0.159 phi p IAZ by A, where phi represents the flux, P represents the number of poles, IA represents the armature current, Z represents the number of conductors, A represents the parallel path. So here 0.159 will be constant, number of poles will be constant, Z will be constant and A will be constant. That's why your torque majorly depends on flux and the armature current. Similarly, if you are going to consider the equation, EMF equation, E is given by phi p n Z by 60A. So if you want to write the equation for n, so it is E into 60A divided by phi p Z. 60 is constant, A is constant, P is constant, Z is constant. So that's why your speed is directly proportional to E and inversely proportional to flux phi. So from this we can define the characteristics. Now if you consider with the torque and the armature current characteristics first. So from the relation we have written, a torque is proportional to the flux phi and Ia. So now let us consider your torque is proportional to flux and Ia. So if you consider for that, right? So as we know that, again here we have two types of motor, DC series motor and for the shunt motor. Let us go with the series motor first. If you're going with the series motor, we know that a torque is proportional to both the flux and the armature current, but your flux depends on the armature current. From that we can write your torque will be directly proportional to Ia square. So from this relation, so your torque varies directly proportional to the square of the armature current. That's why we are going to get, when we are going to increase the torque current, your armature current also increases as a square of that. Now let us go with the second one, the speed versus the armature current. From the relation we already know that the speed is directly proportional to back EMF and inversely proportional to the flux. Now if you are going to consider with this, so we know that the equation for EB is given by V minus IA/RA in case of a DC series motor. So whenever we are going to increase with the armature current, right? Whenever the armature current increases, the drop across IA/RA also increases. But here we have minus IA/RA, so your minus IA/RA will decrease. As it will decrease, your back EMF will decrease. Since your speed is directly proportional to the back EMF, as a current increases, speed also decreases. Now let us go with the last characteristics, a speed versus a torque. Directly we don't have a relation between a speed and the torque, but we have a relation between the speed and the armature current. So if you consider with the speed, it is directly proportional to EB, where EB will be inversely proportional to IA. And if you consider with the torque and the armature current, your torque is directly proportional to IA. From this relation, we can interlink that your torque will be inversely proportional to speed. That's why when torque increases, speed decreases. This is in case of a DC series motor. Now, if you consider the same thing for the shunt motor, so again here also we are going to discuss about the torque versus armature current, speed versus armature current, and the speed versus the torque. So here also the concept is one and the same. Here the torque is proportional to phi and Ia, but we know that in shunt type of motor the flux will be constant. Why means the shunt field winding will be connected in parallel with the supply voltage. That's why the flux will be constant. So your torque is directly proportional to only Ia. So it is both directly proportional, it is linearly proportional. So when current increases, torque also increases linearly. That's why we're going to get the linear curve here. Next we are going to consider the speed, which is directly proportional to EB and inversely proportional to flux. But in shunt type of motor, flux is constant, so we can consider only speed is directly proportional to EB. But we know that EB equation will be V minus IA/RA. So as IA increases, a drop across IA/RA also increases. As drop across IA/RA increases, here V minus IA/RA decreases. So that's why we are going to get the curve as Ia increases, your speed decreases linearly. Similarly, between the speed and the torque, we don't have direct relation. We can consider torque is directly proportional to Ia and speed is inversely proportional to Ia. Using that relation, as torque increases, a speed decreases linearly. This is what the characteristics of a DC series motor and the DC shunt motor.